All right, let's get started. Hello, my name is Angelique Lentjes and welcome to our webinar Practicing Responsible AI. This webinar, as part of the Professional Education Week, is hosted by TU Delft Learning for Life. We offer a broad portfolio of courses for professionals in a variety of themes, including AI, data, and digitalization. The next hour, you will be brought up to speed on the latest insights on how to use AI in a responsible way by our speakers, Stefan Buijsman and Cynthia Liem, both Associate Professor at TU Delft. Please raise your questions in the Q&A and we will try to answer as many as we can during the webinar. Cynthia and Stefan, welcome to you as well. Please go ahead, Cynthia.
Thank you very much. So, good afternoon in the Netherlands. I know this is a global audience, so good evening or good morning if the time is different for you at this moment. Very happy to share some of our work with you. I myself indeed am an associate professor at TU Delft. I am trained as a computer scientist. And if we discuss this question of responsible AI, the first thing I'd like to point out is that actually we come from a lot of different methodological schools of thought that in discussions of AI may be blend without us being so articulate about it. So there is, for example, science, the idea of measuring the world and having your laws of physics underneath it in terms of approaching a certain truth. There's engineering, which often is about constructing things with craftsmanship. There's designing things in such a way that it's usable, that it's useful, that it's accessible. And of course, elements of the arts and the social sciences may even enter if we are going to work in a data-driven way. So I'm mentioning this now because later on, lots of my discussion will be about what would be a good answer to optimize for. And there may be different takes from these different methodological schools may play roles there that we are not always, again, as explicit about. As another word of warning, maybe we are in a world that likes to measure, that likes to work on data, but there have been warnings actually in economic theory and in anthropology that have now been quoted a lot. Goodhart's law, rephrased by Marilyn Strathern, when a measure becomes a target, it ceases to be a good measure. Because as soon as you datafy and numerify something and you optimize for it, often there will be perverse aspects if you only optimize for that. So that's another thing to be aware of if we want to work in responsible ways, that we keep understanding where things might get perverse or different and where we might want to mitigate as human beings. Before going there, though, and my colleague Stefan will later on also take over from me for an ethics perspective, I want to start with a basic term that as a computer scientist, you get basically often in the first year of your schooling, and that now in public narrative has been repurposed a lot, the word algorithms. If I now put it before audiences very often, they have all kinds of associations, Netflix, Google, things that recommend things to you. But an algorithm is nothing more in its basic form than a kind of recipe. It's a procedure to get from a starting to an end state, where you define how you start, you define how you end, and you define how you get there. So one thing that's important to note is if you ever speak to someone who has a technical computer science background and you speak about needs for algorithms, they may be thinking at a very different level than you. And one important aspect in this is also that algorithms are not necessarily smart. In the AI discussion, this does seem to be conflated a little bit, but I can think of really stupid and ineffective algorithms. Say, for example, that I have these houses which would have numbers on them, and I'd like to sort them in ascending order. So the lowest number I want to have on the left side, the highest one on the right side. A stupid way to do this is to take all my houses. The beginning state is they are not sorted. I throw them in the air randomly, and I hope that they end up in order. And if they don't, I keep repeating that until they are in the right order. Now, with two of these houses, after a few throws, I will get there. If I have four, it gets more difficult. If I have 1,000, I can throw for a very long time. Not very handy. Something that is smarter could be that I start with my houses. I start on the left side and I compare two neighboring houses. And I make sure that the largest number out of those two goes to the right side. So I keep things as they are. If the number already was the higher one, I swap them if the leftmost house had a higher number. And if I keep repeating that throughout my house row, at the final stage, if I had seen all the houses, I know that the largest element will be on the right side. That means that next time I have one house left to check, etc., etc. So that's a smarter, it's not the most efficient way of doing it. We call that double sort, but it is a way to sort where you, however, are more guaranteed to get your houses in sorted order faster than if you just throw them in the air. Often, if we think about constructing algorithms as computer scientists, we think of efficiency, we think about what's efficient for large numbers. We also think about general applicability. What is applicable to any problem in which we can agree on a way of ordering? So not just houses with numbers on them, but anything that has a number or anything that can be put in alphabetical order, etc., etc. There are some underlying values in this way of thinking. For example, efficiency. As I said already, you want to have some thought about when you end up with your final state. Generalization, I don't mind if it's a number or a letter, as long as I can sort it. Scaling up, I want it to work not for 1 or 4 houses, but also for 1,000 and maybe 1,000,000. And then using this exact same procedure, whatever I sort. Now, this may literally turn people into numbers, depending on what you are sorting then. And that's again where questions of responsible computing come in. But at the same time, this also may provide us with some useful mirrors, if I may call that, to our thinking. Because being precise about how a routine should be, constructing an algorithm, that's difficult. If I would ask you to very exactly write down how to make a peanut butter and jelly sandwich, and you write down the recipe, it's very likely that you will forget critical elements in that, because we as humans just fill in what we have to do. And for that, I do recommend for you, in the interest of time, I won't show you any videos right now, but to look up the exact instructions challenges on which there are videos on YouTube. Typically, it's parents that have their children explaining to them how to make such a sandwich. And it's really funny because you see how much we then forget and what you have to explicitize. Now, this is why it's difficult to make algorithms. This is why it's difficult to program. This is why in code also we get bugs in our code very often, because we forget when making a routine sometimes some critical details. And that's been a reason why machine learning also became popular. Methods to learn patterns from data and from labels. Say, for example, I want to distinguish cats from dogs. I know that cats have longer tails on average than dogs. I know that dogs, however, have a higher shoulder length. So if I would look at the shoulder height, I should have said of dogs and of cats and of the tail length, I should get clusters where the cats end up in one corner, long tails, lower shoulders, and the dogs in the other one, higher shoulder, lower tail. However, in practice, we typically don't interpret to that degree if we do data science and machine learning. We rather like to abstract. So whatever these things are, we have a red and a blue class, and we want to distinguish them. Now, in this particular example, you could say, well, if the data distributes this way, we could just draw a line, and then we can separate the red from the blue. But in such cases, you cannot. So many theoretical machine learning classifier algorithms, the algorithms that learn how to fit the data, have different strategies of making sure that whatever you get in, you can fit the red to the red and the blue to the blue. And there are lots of different strategies to that. These are just illustrations of different classifiers in the scikit-learn package. Every column is a different learning algorithm. On the left, we, for example, have nearest neighbors, where you look at the closest points around you and what color they have. And that way you can be very flexible to whatever distribution you see, but you get very fickle decision lines. The second one to the left is a linear SVM. And there you see that, you try to draw lines, but as a consequence, that doesn't always go so well, etc. So this is how machine learning happens. It looks, regardless of distribution, how to fit your data properly. And that's not the full story. Very often we want to use these methods to also predict for unseen data points. So if I have my dogs, if I have my cats, this new data point comes in, and the question would then be, would this be a dog or a cat? And it is closer to the cluster of cats we've seen before, so most likely this would be a cat. Still, at the same time, you probably have to check to make sure. So often we use these predictive algorithms to actually ultimately inform priorities that we want to make. So coming back to this example, we classified here based on data we already saw that was evidence. But say that with this particular example that I showed before, a new data point comes in. They're right in the middle. Is it red or is it blue? That is ambiguous. And depending on what classifier you've used, it may actually give you a different response. A nearest neighbor classifier or a linear SVM will actually give different responses on whether this should be blue or red. And again, actually, the best thing is to really watch and check. Now, we may find patterns in our data sets. This is not red and blue, but maybe stars and crosses, but it's the same idea. And then again, we see patterns statistically, maybe so. And often we are in situations that a lot of new data points come in, like these squares that we see out here. So we've seen data evidence in the past, the stars, the crosses, and then now we have all these squares and they could become stars or crosses, we don't know. But now we are pressured to choose 5 data points out of that because we don't have capacity to check for every square what it will become. And say that we give interpretation to this, say that there are interpretations to our labels, and this is data that is about fictional human beings. Now, I haven't given interpretation to the axes yet, but in true interactive education fashion, I am now inviting you to scan this QR code, where I have an exercise behind it, where 3 times you will get different interpretations to your axes. And you're asked to pick 5 data points then, 5 squares, that you think most interesting for the given case. So if you scan this or if you type in that URL, you go to a Qualtrics survey, and I do invite for you to participate here. I'll give you a few minutes to get through that. As said, you will get the question 3 times. All right. I get some indications that people may actually already be finishing, so let me actually do that. If you didn't fully complete yet, it will remain open, so be welcome to still complete it later. Anyway, I 3 times gave you the same data. The only difference has been the text that I put around it, but in terms of where data ended up, it would have looked like the same measurement if I wouldn't care about that. And what we see is that indeed classifiers would not distinguish at all. We see a 2D positive trend to the right top. So you would, in principle, pick the items to the top right as stars then. But did you do that? That's the question. I ran this exercise with many audiences, and what we do see is that humans actually will focus differently for these 3 different cases. I even hear separated answers from those who consented for their data to be reused. On the top to a very technical data sciencey audience, and lower to audiences that explicitly did not have technical backgrounds and just got into the question of data. And you see that actually in all cases, the 3 columns are the 3 questions I put, especially the last question that is about who you select for the interview. You see many people saying one of the dimensions, that physical length, actually shouldn't have been a differentiator in who got selected. Historically, something happened there, but we don't want to use that. And you see these types of justifications going on. There is most agreement on the leftmost one, the first case you got about the student admissions, but even on that one, of course, people who have high grades and high motivation are very likely to complete the course. Then at the same time, if that's the only people you would admit, you will take out the ones that might blossom a bit later, or might have to develop into something, well, maybe they didn't have enough access before. So here again, actually is a policy choice to make. We're purely on data or optimizing for the ones who make your final diplomas very fast. It might actually wield out another part of the audience that you might also care about. So this is where this question of what you measure, what you predict, and what you do with it in policy might actually be different questions that really will need domain expertise. So we shouldn't only apply machine learning in the focus that we typically would have, that there is data and some outcome and we optimize for it. I would argue that's often too narrow. Domain experts are important. The justification of what data goes in, how the application looks, And even more so, I do want to emphasize that data also only is a projection of some bigger problem that materializes into measurements. So having discussions about that also is very important in many applications. Even more so because your prediction often is part of a bigger, often socio-technical system. So decisions that you make in the end there might be very different from predictions you make. As one really simple question about right answers in a task that seems very objective. Say that I want to make a visual object classifier. And for that, I have a lot of different possible answers I want for my classifier to give. And I go around the internet and I ask people, is there something I want to classify in this image? Like, is there a bug in this image? If many people say yes, then as a consequence, I mark my data as such. The column corresponding to a pug gets a 1. All the other potential columns of answers get a 0 because I have evidence this should be a pug. And then I nicely have a mathematical representation I can give to my systems to learn to predict that for this particular input image, I want a vector out that gives highest odds to this image being a pug. We've seen a lot of systems trained like this. We've seen, however, also that this really implicates how your classifier would respond. If I give this image to a classifier or to different classifiers that became very popular in the deep learning age, they will all super confidently say that this is a castle. And yes, that was the right answer. But the second possible outcome, monastery, has much lower odds. It's really, the classifier is optimized to give a 1 on the thing it's most confident about. What you then see is that it won't classify this castle as a pug, it shouldn't, but it also won't see the concept of a wall in there. That was another possible answer that could have been given in this particular classifier. And why is that? Because walls look like these images. Very specific captures of walls in an isolated way. And in terms of object classification, this is correct. If you see that image, it's a castle and it's not a wall. But say that I would put such a classifier in a self-driving car. And the car knows it should stop when it sees a wall. Well, if I would tell that to a car and it's trained like this, it should have to get awfully close to walls in order to detect this. And I think that's not something you would want. So when do systems perform well? Very often we do optimize for accuracy or now loss in the generative AI age. So something that looks like good answers that were there before. Accuracy, how often am I right? How often do I correctly classify according to the label I gave before? But what we then tend to forget is how bad is it to be wrong? And there we see already in the self-driving car an example that probably these cars make less mistakes than humans do because humans are honestly not very good drivers. But still, there are good reasons to not allow them on the road, and it has to do with accountability. If something goes wrong, who do you blame? What's going on then? So here, it's not only about how often you are right or how often you don't cause an incident. It's actually much more about if an incident happens, what do we do then? Also, this concept of false positives or false negatives, like do we coincidentally select something as an answer, but then it's not actually true? Or the other way around, do we forget to select something where we should have? Classifying a student as not having high odds to complete while they could have, compared to admitting someone who will fail. And here, in different cases, you also see different weighings happening. Like if you want to treat patients who might be ill, if you doubt, in case of doubt, actually, you may want to still go forward, even if you're not sure if the person is sick. Having them going to treatment is probably better than leaving a sick person unrightfully not treated. The other way around, I helped a lot on commenting on risk monitoring stories. In the Netherlands, we had a bit of a history with discriminatory algorithmic risk profiling on whether people were committing fraud. We see stories like that more broadly in the international sphere. And there, the injustice often happened because the same people kept being classified as being potentially high risk. And they were people who looked like, who had similarities to people who were halted before, time and time again. And at the same time, people who were not similar to that were never halted because there was a feedback loop really specializing into a particular group. So there, the false negative story maybe is actually having bigger weight, that you let people go free that might also need checking, while another group carries a lot of burden to being suspected all the time. So these are just a few examples that I wanted to share with you on how this question of what we optimize for and what is right and what is wrong can be very nuanced. And if you want to act responsibly, you have to think about it more thoroughly. This is also the moment that I will hand over to my colleague Stefan. But while I do that, I am, of course, very happy to already maybe quickly answer some first questions from you, and otherwise we can do that later.
So far, no questions, Cynthia.
So far, no questions. Then things were hopefully very clear.
That means that Stefan can set up his presentation. There is one.
Yeah.
Before you start, Stefan, I will give you the question, Cynthia.
Yes.
Can you share some AI tools linked generic and specific, which is open source for any design application, apart from many available in the internet?
Oh, my goodness, that's a big question. So,
yeah.
Any AI tools open source on a particular problem?
It says for any design application, and not available already on the internet, apart from many available on the internet.
Right.
I don't know if this one is
right.
Is an easy one to answer.
Right. So the ones that can be shared, I do think are on the internet. I mean, what's useful maybe is to share a few guidelines or responsible AI checklists if that's not yet on people's radar. So at least that is something I can put in the chat while Stefan is presenting, maybe. Yeah.
Yeah, that's good. That's fine. There is another question. Responsible from whose point of view? Decision maker, society? These may contradict at some point.
They totally do. And also here, I think the morally just take would be to not only think of your own interests, right? So often, of course, certain stakeholders are more clearly in the picture. I do think Stefan will also touch upon this story in his part. But in this idea of being responsible, I do think it is about taking care of all possible stakeholders you can think of that may be affected by your technology, not just the ones commissioning you to do something in a particular way. And then again, as an engineer, if you build these systems, also being accountable for the choices that you make and knowing why you make them or what you then might not give priority and maybe then even mitigating for that if you don't do that.
Mm-hmm. Yeah. Okay, well, another one. Let's see if you have something wise to say about that. Where do you see quantum computing fitting into the evolution of AI?
Yeah. I am not that deeply into quantum. Of course, in terms of computational opportunities, it would open more opportunities to do things. So I would say on that end. But indeed, it's not my main trade. So that's also something I will not extensively answer here. Yeah.
Okay, well, Stefan, if you're ready, then we can start with your part.
Yeah, absolutely. And I see there are more questions coming in, but we'll do that afterwards.
Yeah.
So also please do keep posting questions. We're very happy to have those. Hi everyone. I'm Stefan, associate professor in philosophy at the TU Delft, and also like Cynthia working on responsible AI. And I think it's a really nice handover between the two of us because also from the philosophy perspective, a lot of the questions here are about what are we optimizing for. And so to give you a practical example, where exactly this optimization goes wrong is Amazon. A couple of years ago, when they started their same-day delivery service, they used an algorithm to determine, okay, which areas are we going to offer this new service in? And they optimized it for their return on investment. Very predictably, they wanted to make sure that they recover as much of their investments as quickly as possible. So they calculated based on all of their client data, okay, which parts are people going to spend the most money on Amazon products if they get their package a day sooner than they currently would. Now, of course, that's something that works perfectly well. They had all of the data to do this, and they got an algorithm that very accurately managed to predict exactly what they asked it to do. So to predict this return on investment. The only thing is that I think, as Cynthia also nicely pointed out, they didn't look at the overall problem and the really broader set of constraints that we want for these systems to adhere to when we develop them and deploy them. So what happened in this particular case is that they came up with the following maps in different cities in the US. And the areas in blue that you see, they got access to same-day shipping. And all of the gray areas, which, if you know the US a little bit, you can probably already figure out are exactly the low-income, primarily African-American neighborhoods of these cities. So the Bronx in New York, the Roxbury right in the middle there in Boston, they were excluded from same-day shipping. And in a sense, that's exactly what we asked the system to do, right? I mean, if you don't have a lot of money to spend in the first place, then probably you're not going to be buying a lot of extra Amazon products if you get them a little bit faster than you otherwise would. But what happened is that by simply focusing here on the accuracy of the system and not thinking about, okay, but what are we really doing with this system? They reinforced the ethnic divisions that were already there in the US. And this was particularly problematic for Amazon here because regardless of where you lived, you paid the exact same thing for Amazon Prime. So it's just that the people in rich areas got more for their money than the people in the poorer areas of these cities did. And so very shortly after this became public through investigative journalism, Amazon moved back, decided to offer it in the entire cities because they didn't really have a good answer for why they suddenly made decisions in this way. So with these AI systems, really practicing responsible AI often comes down to thinking, okay, what is the broader set of requirements, and then making sure, that's I think the practicing part here, that they end up in design of these systems. A lot of these decisions really are made in the early stages, data labeling, data collection, and algorithmic decisions. And that's what filters into whether the system will do the right kind of thing or not. To give some non-AI examples that I think are really nice to illustrate that this is really a design issue. Here are some bridges also in New York on Staten Island, which were constructed around the 30s. And they are all positioned very strategically around a brand new park that was just designed by the city planner of the time. And each of these bridges is low enough for all of the private cars that you see on the picture, but buses are too high to be able to pass under these bridges. So by the design of these bridges, and it was very intentionally done at the time, it's impossible to get to this new park through public transport. The bridges are simply too low for the buses to get there. And so the park excludes certain parts of the population of New York. By design, and the bridges are still there, and it's still very difficult to get to this park without your own car. So you can't really easily fix it afterwards. And that's true for these bridges. It's true for, well, these kinds of benches where we don't put the armrests there because they're so comfortable, but we put them there because planners of these parks wouldn't want homeless people to sleep on them at night. So there too, it's design decisions that feed into, okay, is this responsible or not? And we can tweak those, we can change those. But the question for being able to do that is that we need to be very explicit on, okay, what is it then overall that we want to achieve with these systems? And so that's, I think, also where the question from a couple of minutes ago comes in. Okay, you should try to identify all of the people who are going to be interacting with this technology, who have a stake, who are going to be affected, and look at what's important to them, what's valuable to them, and how can we balance that into our design of these systems. And the European Union has made a really nice start on this by saying that at least for systems deployed here, we should think about things like human agency and oversight, also to really make sure that we remain responsible for the decisions that we're still taking when we have AI systems in place. Robustness, safety, of course, and privacy is a long-standing priority in the EU. But also things like transparency, non-discrimination, and environmental well-being. Each of these are valuable, and they are not automatically included if what we focus on with AI is just how accurate the system is. In fact, a lot of these can even conflict with the accuracy of the system, meaning that you'll do worse typically on something like non-discrimination, if you really optimize only for the accuracy of the system. The challenge, of course, from this is we have a very nice list of all of these values, but unless we make them concrete, unless we really make them tangible, they don't really mean much more than that there are nice words on paper that we can agree on, but might mean very different things by. So the difficult thing to then practice the responsible AI is to make this translation from those high-level values, things like privacy, non-discrimination, transparency, all the way down to the level of design requirements, where we really have a way of designing the system, changing the choices that we're making during the system design in order for it to better fit these values. Now, that can still sound pretty abstract, so I'll try to give you a couple of examples of how we see this happening, and then hopefully that will make things a bit clearer. To start with, I think privacy is always a really nice example because we have a very clear sense, at least in legislation, but also in theory and in ethics, of which things in privacy we find important. So as you can see here, you have this overarching value of privacy, and often what we find to be important for privacy is 4 different things. So first of all, we care about mitigating risks. So if your private information is leaked, then people can use that to, for example, commit identity theft or to scam you out of part of your money. So there's really a tangible financial, personal risk that you run by people knowing information about you. And we can then say, okay, well, there are lots of design things that we can do to reduce that risk. We can make the data that we're collecting more anonymous so that it's harder to link it back and to really harm you personally after this data was leaked. And for example, you can do that by clustering data or storing less sensitive data in less detailed ways. Again, to try to reduce these risks that you would be running. That won't be doing everything for privacy, so it could still be that we've mitigated all these risks, but that your autonomy, so your feeling that you can make choices freely without constantly being watched, is under threat. So if there are cameras on every single street corner, then no matter whether the data is nicely anonymized somewhere, you can still have the feeling that you are being watched and you'll make choices differently. And we often want privacy exactly to be able to make these choices ourselves without anybody else interfering. A third option then that we could care about is control over our data. So if you give data to a doctor about your medical information, for example, then you don't suddenly want your insurance premium to change. So you want to have some control over where this data ends up and who's doing what with it. And then finally, what we often also see privacy being used for is to prevent unequal treatment. So there's the idea that if we don't know your gender, your ethnicity, and so on, then we can also not treat you any differently because of that. And for a lot of standard decision-making, that's absolutely true. But of course, for AI, now with systems becoming more complex and being able to use lots of other information that might not look so personal in the beginning, it's becoming much harder to make sure that this equal treatment is respected just by not showing your gender or ethnicity to a system. So that brings me to the second value that I wanted to touch on today, namely exactly this fairness. So as I said, it's really difficult now to say that a system is fair just because it doesn't know any personal information about you. It might still make very different decisions depending on genders by, for example, looking at first names or looking at writing style. There are lots of different options for how this could happen. And so the challenge here, like with all of these values, is to figure out, okay, what then exactly do we mean with this fairness? When do we think that one of these systems is treating us fairly? And this is, in a way, quite difficult because we have lots and lots of different options. But it's also something where responsible AI actually helps us to refine, okay, what do we think fairness is? So to give you some concrete, really technical options, right? So one of the things that you could do or could mean with fairness is, well, to go back to a bank example that was also used by Cynthia as, in the interactive exercise. If we have a bank that's trying to figure out who should be getting loans or not, then one way to say that, well, we're treating people fairly and equally is to say that, well, these two different groups, relatively rich people and relatively poor people, should just get loans equally often. And that's one very valid way of saying that, well, we have equal treatment because they're getting loans equally often. It's probably not the one that you want to be going for, because as you can see here in the figure, there's a really big difference still between the groups in terms of how affordable these loans are. So here we have 3 out of 4 people who get a loan that can actually afford it. And in the other group, there's just 1 out of 4 that get a loan that can afford it. So you still have differences, but you're treating people equally in one way. So it's fair in one way and not in others. Now, there are lots of other alternatives to do this. So you can, for example, also look at the accuracy at which we're doing this. So whether here half of the people who can actually afford a loan, so there are 2 who can afford a loan and won't be getting one, and there are 2 people who can afford a loan and won't get one, and will get one, sorry. So there the accuracy is the same for both groups. In both cases, half of the people who can afford one will actually get a loan. And then vice versa, you can also look at how many mistakes we're making. Now we have all of these different options. Because of all of this technical research, we now also know that you really have to choose between these different options. So you can't just say, well, I want all of these different things, all these different kinds of equal treatment at the same time. We have to make a decision, okay, which of these 3, or actually, if you're looking into the literature, there are something like 20 different alternative definitions that you could go for in terms of equal treatment. Which of those do we really intend, and do we think is the most important one for the use case that we're looking at? As Cynthia also already foreshadowed, that's really use case dependent. For loans in this particular case, I would, for example, say that you don't really want the 2 that you're seeing here. So you don't want equal number of loans, and you don't want this equal accuracy, even though they might be very attractive. And the simple reason is that defaults, so getting a loan that you can't afford, are often very expensive and very costly. So if you model these different situations out, then you see that inequality in society, so the income that people actually have, their wealth, will get less equal over time if we just give people the same number of loans, because you have all of these people here who get loans that they can't afford, and that's very expensive for them. So what we probably want to do in this particular case is to make sure that we don't make more mistakes for the group that's worse off than we do for the group that's more wealthy. And then, of course, try to do as well as we can and as accurately as we can within that constraint. But that will really depend on the use case, what it means to get it right, what it means to make a mistake, and what kinds of opportunity costs would be there if you don't get something that you should have. So these are some of the choices that we have to make. Of course, the challenge then is that very often we can find multiple things important. So for example, we can say, oh, well, equal treatment, fairness is really important, but we also want the system to be accurate. And as a bank, you probably want to make profits. So that's what you're seeing here in this figure, in this table, that actually that really can conflict. So what you have to choose between, this is again a nice modeling study to quantify that a little bit, is whether we want equal treatment. Those are the 2 columns in the middle, where you have in bold 2 cases where you have 75% extra equal treatment. So we're doing really well on fairness and making sure that people don't get discriminated. But the consequence of that is that the profit of the bank goes down by about 30%, and that the accuracy of the system also decreases by 9%, which in this case is 9 very consequential percentage points for this bank. And vice versa, in the case where we have very little decline in profit, right? So you have one case where you have -4% in profit in bold, then you have very little improvement in equal treatment, only about 10% on the different metrics that you're seeing here. So we have to choose, somehow balance these different values that we have. And in this particular case, I would say that you, again, try to look at, okay, what's the actual impact on people? So you look a little bit beyond the numbers and what does it mean? And then even here, you'll see that just going for fairness full out typically is bad also for the people getting loans. The 8.5% accuracy that you lose could also mean that lots of extra people get loans that they can't really afford, and that's why the profit is plunging. So that actually this could be a bad decision to make as a bank, both for yourself as a bank and for your customers. So here we have to try to quantify what is the actual impact we're having on people and what do these numbers then mean. Now, fortunately, we don't always have to make these, so we have to make these kind of difficult decisions, really try to figure out the trade-offs and somehow find, okay, what optimal solutions between good accuracy and good equal treatment can we find, and then how do we choose between those optimal solutions? And that's an ethical discussion to have in the end. But because we can quantify it, we can have it much better. Sometimes we don't have to choose. For example, you also often have a challenge with privacy when you want to have equal treatments. So we just saw that privacy can require you not to have personal data, so not to have data on gender and ethnicity and so on. But if you want to make sure that your models are actually enforcing equal treatment, then we need this kind of data. We need to know what people's ethnicity and gender and so on is. So that's another conflict. And here, I think the really nice thing is that there's innovation, technical solutions that can help us be more responsible and actually meet all of these criteria at the same time. So we don't have to choose if we, for example, use something like synthetic data where you generate, like the deepfake images that you're seeing here, fake people who we can use then to make the algorithm more fair. But we won't be violating their privacy because those people don't exist, and we don't need really sensitive personal information, at least at that stage, once we have this synthetic data, to be able to still allow for equal treatment. Now, of course, there's always a catch with these kinds of solutions. So you have to, at the same time, make sure that your synthetic data is actually looks like the people that we want to make decisions about, right? So in these two images that went perfectly fine. If you have examples like this that we're training our system with, then your innovation is not really solving the problem. But I think it's a nice example of how also really technical steps can help us meet our ethical obligations and our dedications to responsible AI better. Because we can now do new things that we couldn't do before. Now, the final thing that I then wanted to touch on is that, of course, that's really the technical side of responsible AI, but that very often it's also about this socio-technical system. So the interaction between your AI system and the rest of the organization, the context that we're applying this into. And so NarcScare is a really nice example of how you should not do this. The system itself is something that we can debate about, but in principle is not per se super problematic. It tries to predict whether someone might be addicted to strong painkillers in the US. And if we were to use that in consultation with a doctor to then try to help these people and offer them extra treatment, that might actually be a positive thing. The way it has actually been implemented in the US is that it's there for doctors to look at. Officially, it's not supposed to take over their diagnosis, but in practice, they're expecting people to really use this to deny painkillers to anyone that the system deems at risk. And physicians are legally required to look at it, can lose their medical license, and can actually be criminally prosecuted if they still keep prescribing painkillers more often than the system suggests. So they've put in a really strong, heavy consequence to the score from the system, and then made it almost impossible for doctors to disagree with this system or be critical about it. And it's really those combinations, the kind of role that we're putting the system in, that make it much more problematic than the AI itself perhaps might be. Now, just as you can do this badly, of course, we can always also use this context and the interaction between the AI and the people around it in a positive way. Here's a better, more positive example of exactly that. This is an insurance company in New Zealand, which also uses AI, in this case, to automatically determine whether or not an insurance claim that you submit should be paid out. Now, that could be really problematic, but in this case, the setup is that the system only is allowed to accept insurance claims. So if the AI thinks that, yes, you should get your money, then you immediately get it back. And there's very little in terms of then trying to recover it afterwards. It's just if the system said this, then you're getting your money, and they will do, of course, regular testing to make sure that the system is sufficiently accurate in that decision. But there's nothing bad that can happen from this automated consequence for you as a customer. If instead the system says, no, you shouldn't get this insurance claim reimbursed, then it doesn't have immediate consequences, but instead it goes to an employee who will then do everything about this claim by hand, so that you get a full explanation in case this employee decides that you shouldn't get your money, and vice versa, that there's still a lot of room for them to say that, well, actually, the system simply misunderstood something, it missed some nuances, and therefore the claim should still be paid out. And they do this in about 50% of the cases that the AI rejects. So you have a really nice combination where it only primarily helps to make the process more efficient, but we don't lose this human element and the understanding of the case in the situations where it really matters, namely where we're rejecting insurance claims of people who might really need that money. So yeah, to sum up my bit a little bit, I think when we're doing responsible AI, when we're developing and using these systems, what really matters is that you do have all of these values into the design of the system, whether you want to or not. This is going to happen because it's implicit in a lot of the choices that we're making. And so ideally, you want to be explicit on which values you are considering, and making sure that they are also reflected in your design, so that you can motivate choices in the goal of your system, in the technical functionality, in the implementation in the organization. And that in this case, so also really these interactions with the system are just as important as the AI system itself. With that, thanks a lot. We have a QR code here for you for extra courses and programs, and of course, a little bit of time left for questions to me and Cynthia.
Yes, we indeed have some more questions. So I have here a question. I'll try to summarize it a bit. That's about how regulators can help provide clarity on responsible use of AI. So what can legislators do better to provide clarity to developers of AI?
Yeah, I think that's a really good question, because the regulation in Europe is still relatively unclear in terms of what you exactly have to do. What I think is the most likely step forward is that we're trying to look at cases, so that we give examples of what we mean with this in particular settings. So for specific AI systems at specific companies or in specific industries, and then show, okay, how do we interpret these requirements of transparency and fairness and so on. It's very difficult to give general principles that will suddenly cover all of this. And a lot of it is really just having the conversation and being explicit about this, I think. So I wouldn't expect it in terms of strict guidelines, but much more this dialogue and setting these examples of, hey, this is how we think it should be done. I see Cynthia nodding, so I hope you
agree. Yeah, and then linking to the links that I also shared, right? You see with the AI Act that there's mostly been a push just to be more aware of whether you might contribute to something that is high risk, and to, well, force a bit more that if you are contributing to that you are accountable for that. And all these guidelines towards trustworthy AI typically are self-reflection dialogue starters. So a lot of that is meant to inform you on how can I make this better, rather than saying you shall do it this way or that way, because very often there is a lot of contextual choice to be made there. So I think that's a good example of how regulation helps to nudge towards actually doing this, but at the same time, it doesn't fully strictly put a template on you, and there is some room there.
Okay, good. Someone is asking about understanding privacy as a value and how this relates to the norms that are part of that, especially to equal treatment. Equal treatment as value, would it be better to use lawful processing of personal data as value instead?
Yeah, so fair enough. It's always tricky to give really good formulations to all of the intermediate levels. So the reason why I picked equal treatment there is because of the interaction I think you see between privacy and equal treatment. So I agree, fairness and non-discrimination is a value in itself, but the motivation that people give for privacy and excluding personal data from data sets very often is that we want this in order to get better equal treatment. So there's a bit of an instrumental interaction between the two. And yeah, I agree, the figure simplifies that a little bit. But that's, I think, where it comes from in both the regulation and in the theorizing.
Then there is also a question about, is local AI more responsible than cloud AI, or is it not easier to have it more responsible?
I think you have more control if you develop it yourself. At the same time, that can also mean that you have to be very aware of all of the choices that you're making. So it's a bit of a trade-off. If you have the expertise in-house, then yes, it's much easier to be that explicit about this and monitor it yourself. On the other hand, just knowing what you want out of these systems and then hoping and then trusting and verifying through documentation and so on, that the provider is doing this for you in a good way, could also be a better choice if you're a smaller organization without these capacities.
Okay. And then someone is asking, can you name an area where AI has been highly beneficial? And can you name an area where AI has been highly harmful?
Ooh, maybe Cynthia has very good ideas on this, but I
Well,
think, yeah.
You gave some examples in your talk as well, right? So I guess areas, well, of course, in high stakes critical decisions, right? Medical decisions, such things, it can have a lot of benefits, and humans can be really biased. At the same time, that also means that you can very quickly maybe scale up things in ways you don't want. So you have to be really careful. For me personally, I think the most convincingly beneficial applications have been more on the physical natural sciences realms, things like the protein folding stories, where just your language, your vocabulary, the laws of physics you're rooting in or biology are very well known. So indeed, with a lot of data, you actually get a more directed answer in some way. Where I think on the social sciences side, like things like criminality prediction, there we've seen very biased, scaled up harm being done where people then hid behind its data, so it's subjective. So I think those are a few extreme examples I would bring up, but then again, Stefan, you can certainly add to that too.
Yeah, no, but I agree. And typically the more social context is involved, the harder it gets to really make good AI systems. So if the situation is more clear cut, and I think the physics examples are really nice cases where we don't have all of the social context complicating matters, then it's fantastic.
Then there is also a question about the use of AI for candidate selection in job applications. What do you think about this? Is there a huge problem of transparency? what would be your comment on this?
Maybe I can take that as I did a bit of work in there. Yes, I do think it is problematic in that that's another case in which people do seem quite overwhelmed, that there are lots of potential choices and you need to make a selection. But typically the data you had so far is humanly biased. You don't quite know how alternatives should have worked out. And yes, I mean, it's still a bit unclear how prevalent it is, but I do hear many suspicions that now it's becoming way more integrated in many screening and hiring processes. And I've heard stories about our PhD candidates who've done data science PhDs and then couldn't get into data science roles because they weren't a junior data scientist after their master's, seemingly, and they had to optimize wording in order to actually get invited. So yeah, there are big risks there, and I feel that that's one of these questions where we don't actually know what the good candidate is. At the same time, I also see benefits of using technology to counteract potential human bias, but then you have to very deliberately design for it. So not only repredict what a human did before, but maybe counteract or create some friction in the process, like, hey, if you like that candidate, maybe you should also look at this one that you didn't look at.
Oh, thanks. Maybe one more, is that okay with you? I see here the social context is the most important, particularly in public administration. How do you see regulatory to support responsible AI in the public sector?
Yeah, so at least the regulation holds just as much for the public sector, and a lot of the public sector systems that we are worried about and have seen scandals of in the Netherlands and other countries are now high-risk systems under the AI Act. And that also means, I think, that you really are pushed into reconsidering for the public sector, okay, what do we want to use these algorithms for? And so the kind of risk profiling might not be always the most suitable thing to integrate a system into that we then start really blindly relying on if we're unlucky. And instead there might be other parts of public service and public services that are more focused on supporting people or spotting when someone might not understand exactly how to fill in a form and then offering some tailored help that are more suitable. But yeah, I think that's an ongoing question and something that also, well, both Cynthia and I are working with parts of the public sector to try to answer.
Okay, well, thank you so much. Thank you for your thoughts, your insightful presentations, and thank you all for joining us. Well, if you would like to know more about this, please reach out to us. You can also stay connected with us through our socials, and perhaps we see you another time. So thanks again. Bye.
Thank you.
Thank you.